This is lecture number 14 of the course AU 203 Statistics and Quality Control. We have already done a binomial distribution, and today we will go into the expected value, calculating the expected value of a binomial distribution and the variance of a binomial distribution. Expected value shows the measure of central tendency and variance shows the measure of dispersion. And then we will go into calculating the probability distribution, cumulative probability distribution, or the binomial probabilities using using the tables, cumulative distribution tables. And then we will go into calculating the same thing on Minitab. Okay, so we know the probability mass function for a binomial distribution is this. We know the definition of probability mass function is nothing, just a mathematical function for a given random variable. It gives us the corresponding probability. And here we know that the shorter way of writing down a random variable x which is binomially distributed with the parameters involved are number of trials, and p is the probability of success, and its corresponding the mathematical function which gives the corresponding probability against each random variable, each value of the random variable rather, will be able to calculate. For example, if x is 0 and n is 5 combination x, and whatever the probability of success to the power x, and this how we can calculate the probability for capital X equal to small x or particular value of a random variable. And we will be able to calculate the probability for any value of x. Okay, what we are interested in? We are interested in the expected value of a random variable, and we know the expected value of a random variable is nothing, just the score or the value of that random variable multiplied by its corresponding probability and take the sum. We will be able to get the expected value of a random variable. Let's say here our random variable is a binomial random variable, and its corresponding probability can be worked out through this probability mass function. So what I have done is nothing, just x multiplied by its mathematical function, which is this PMF. So x multiplied by px and take the sum, so we will be able to calculate the expected value of a random variable. Okay, now there is some mathematics related with factorials in order to simplify that expression, but this is the formula for calculating the expected value of a random variable for binomial distribution. Okay, what I have done here is n combination x can be written in this form using the formula for combination n factorial over x factorial divided by n minus x factorial, and the rest remains the same. And the value of x would be starting value from 0 to n, because you know x is here is a discrete random variable and a special class of random variable which is a binomial random variable satisfying that 4 conditions we have already elaborated in previous lectures. Here what I've done is x is here, x is here. This x factorial can be written in this form: x into x minus 1 factorial into n minus x factorial. So at this point we have a provision to cancel out this x. So in the next step we will cancel out with x, and we will be ending up with so x is gone here. Now you have n minus 1 factorial, and here instead of x you have x minus 1 factorial into n minus 1 factorial. Okay, then here I make it some deliberate common, because n is here and p is here, and probability of success is nothing to change when your number of successes are different. So they can be taken as a constant and taken out common. So n and p, n is already there, but p we are doing it deliberate common. So let's say if I take it common, then this p would be p to the power x minus 1. And the good thing is always whenever you do take the common, multiply it with this thing, and are you going to get the same thing? So multiply it by np. So n is here, p multiplied with px minus 1, it would remain p to the power x, and the rest remains the same. If it is the same, it means it is a correct common step. No? So this is always you need to check whenever you take a common, multiply together into see whether you're getting the same thing. Is always a good habit. Okay, here we take a little mathematical jugglery here. For example, we are dealing with n minus x here. So n minus x can be written in this form as well, because minus 1 and minus minus plus 1, minus 1 plus 1 is 0. It is actually the same thing as n minus x, but instead of writing down n minus x, we write like that, n minus 1 minus x minus 1. So if you do this mathematical jugglery, for example, here in this previous problem, n minus x is replaced with n minus 1 minus x minus 1 factorial. Okay, at this point I make a little substitutions here. N minus 1 is here, n minus 1 is here, and x minus 1 is here. I'm using these letters m and y to represent, m is used to represent n minus 1, and y is used to represent x minus 1, so that we could have some simpler look of that above expression. So okay, now we could have some simpler look. So what I have done is everywhere we have n minus 1 that turns into m. So n would be equal to 1 plus m. So n minus 1 would be equal to m. So n minus 1 factorial would be m factorial, and n minus 1 would be m, and minus x minus 1 would be equal to y. And obviously for the limits of the summation, when x is 1 here, then if you substitute x1, 1 minus 1, then y comes out to be 0. So here y should be comes out to be 0, and n would be equal to, for example, if it is m, then here n equal to m, then it would be equal to m here. So all these things have been changed. NP is a common here, and n would be m factorial. This would be m factorial, and same is here. X minus 1 would be y, and this thing would be m minus y, because n minus x to be replaced with this way to write down, and then it would be some neater way to write down the expected value of a random variable. Keep in mind we are starting at here 1, but now 1 is starting point is 0, so 1 is reduced. So once it is reduced, then it would be equal to m here. Okay, I mean, we don't need to go into that. This thing is actually the same as m combination y, and it would be some formula. We have already seen that. If you recall that y starting from 0 to m, then this thing would be much simplified if I take another substitution, that p is I take it as a, and 1 minus p I take it as b, because in binomial formula you know a plus b to the some power. So for that purpose I did that. Here p is equal to a, and 1 minus p equal to b. So I am now dealing with a and b. So this is exactly the same as the formula for binomial expansion, a plus b to the power m, which is m combination 0, and a to the power 0, which is a, and b to the power m. And then next power would be y1, then m minus 1, then m minus 2, then the last term would be b to the power n, because m would be the last term. So the whole binomial expression can be written in this summation form like that. So the whole thing is actually nothing, just the two terms, binomial. That's why it is given a name binomial, because you are dealing with two terms. So here the whole summation in the square bracket can be represented with a plus b to the power m. Okay, here I just substitute back what substitution I have make it. For example, a is p and b is 1 minus p. I substitute this back again. Here np and a plus b is a is p, b is 1 minus p, and p and minus p cancels out. 1 to the power m is 1. Then you eventually end up with the expected value of a random variable. When your random variable is a binomial random variable, the easiest thing is to find out the expected value is number of trials times the probability of success. For example, if you recall back the trial when you have tossing a coin where it was not a fair coin, 0.6 was the probability, and number of trials were 5. 5 into 0.6 would be the expected value of a random variable, or the central tendency of that random variable. So by the way, we have derived this formula for from the basic definition of expected value of a random variable, which is x times its multiplying with its corresponding probability and take the sum to get the expected value. Okay, the same thing we have to do it for variance of a binomial distribution. So variance is nothing, just the random variable is taking the difference with the mean and take the square, and I just do it exactly in the same manner. I'm using the alternative formula for variance. So here expected value is already worked out, n p, so expected value of x is n times p for a binomial random variable. Then expected value formula, we already know that x times its corresponding probability, and now I can calculate the expected value of x square. So just replace x with x square. So I got this. And then the same simplification, that x factorial can be divided into x into x minus 1 into, and then this is cancels out, and we simplify. I mean, this is expected value of x square, but let's say for expected value of x times x minus 1 would be x replaced with x minus 1. So this would be the expected value formula where you are dealing with expected value of x square time minus x. So this becomes the left hand side, and then this is simplified, and here you look closely that once you are dealing with x here, then x was 0. And now what I have done is, since my x starts from 2 here, so because once x is 0, then it would be 0 minus 1, it would be negative number. And if it is x is 0, or if it is, even if it is x is 1, then 1 minus 1 would be 0, and the 0 multiplied by 0, then the whole term would be 0. So that's why I'm starting here my summation from x equal to 2, so that I get a positive numbers. Okay, you don't need to go into this mathematics, but here earlier I have taken np common. I'm taking here n into n minus 1 times p square common. Okay, I take out deliberately common, so I have this expression, and then I make that simplification for n minus x earlier, as I've already done, and then simplify it, and here substitute m equals to n minus 2, and the same expression, the same substitution, simplify, because a and b are binomial terms, so I can get those terms. So here I got the whole term in a plus b to the power n, and simplify that expression, substitute back, so that you got this number. Okay, here you see the variance is expected value of x square minus the expected value of x whole square, and what I can do is expected value of x square minus expected value of x is already this thing, and minus np whole square, expected value is already evaluated. So from this thing I can easily get the expected value of x square minus expected value of x square would be, if you go this term would be plus, So n minus 1 p square plus expected value of x, and expected value of x is plus np, and this is expected value of x np to the power whole square. Okay, if you simplify that, you end up with the variance for a random variable can be easily worked out just by multiplying the number of trials and the probability of success times the probability of failure, because 1 minus p is probability of failure. If sometimes people use q to represent 1 minus p, then the formula for variance of that x particular random variable, which is a binomial random variable, would be equal to np times q. So this is how we have derived the two expressions. Okay, let's see the problem. You have a discrete random variable x which is binomially distributed, so you don't need to about knowing about the conditions where n is 4 and p is 0.8. So the first task is to construct the probability distribution table. So what you need is small x can take different values, because it could take 0, 1, 2, 3, 4. Why not it take 5? Because our trials, number of trials are maximum 4. And if you calculate the corresponding probability by substituting into the formula for their probability mass function, so 4 combinations 0 and then 0.8 to the power 0 times 1 minus 0.8 means 0.2 to the power 4, so you got this number, and then when x is 1 you got this number. So this is how you can make it a probability distribution table, and you can plot it as well. Okay, the next part is to calculate the expected value of that random variable and the variance of that random variable. Expected value of random variable is much easier once you know the probability distribution table. So multiplied with the value of x and its corresponding probability and take the sum. So 3.2 here is the expected value of a random variable, and variance of a random variable can be worked out if you have a knowledge of expected alternative formula. Expected value of x square minus expected value of x whole square. So expected value of x is 3.2, then take the whole square, and expected value of x square is multiplying x 0 means 0 to the power 0 is 0 into 0.016, 1 into the power square is 1 into 0.0256, 2 square is 4 into 0.1536, 3 square is 9 into this, so on. So you will be able to calculate the variance of that. Okay, what we have done is we have used not the formula for calculating the expected value and the variance, but we used the distribution to first develop the probability distribution table, and then we use the previous lecture strategy to calculate the expected value and the variance of that expected value. But you can verify the same thing, because expected value for random variable is n times p. N is 4 and p is 0.8 here. I made a mistake here, so just correct it. Eventually you got the number 3.2. So n is 4, 4 multiplied by 0.8, 3.2. Similarly, the variance of x would be n is 4 and p is 0.8, and 1 minus 0.8 is 0.2, then the variance comes out to be 0.64. So this is how we can easily find out the formula we have derived for expected value of a random variable when your random variable is a binomial random variable. Just multiply it by n with p to get the expected value, and just multiply np into 1 minus p to get the variance of that random variable. So you learn either way of doing it. Okay, now look into the tables by which you can calculate the cumulative binomial probability. So one of the book, this cumulative probability distribution table is given like that. So on the x-axis you have probability, and on the y-axis you have corresponding probability. When your x is 0, you are a certain probability. X is 1, x is 2, x up to k, you are associated with some probability. So the tables given in the manner where n is number of trials, which is for example in this case 5, and k is number of successes. It could be 0, 1, 2, 3, 4 up to 5, and the probabilities are given and their summation of their probability. Summation of the probability means when x is less than k. If k is 3, then it will be probability of 0 plus probability of 1, probability of 2, and probability of 3 is something which has been calculated. If you take an example, then it would be much clearer. Using this cumulative binomial table, when your number of trials are 5 and probability of success is 0.6, you are required to calculate the probability of exactly 3 successes. So k comes out to be 3 here. So x is a binomial random variable when number of trials are 5 and probability of success is 0.6. So always it is a neater way to write down like that, because right now you have only learned one distribution, but you will be able to do more distributions, then things would be mixed up. So one thing is probability of exactly 3 scores. So what we do is first we calculate the probability up to 3. So x is less than equal to 3. So it is actually the probability when x is less than equal to 3, it is actually representing the sum of the probabilities. Cumulative probability it is actually representing. So instead of calculating the formula for cumulative probability, what we do is from these tables, probability of when x is 0, your number of trials are 5 and probability of success is 0.6. So 0.6 is here. So when x is 0 you get 0.010. When x is 1 you are going to get 0.087, which is actually up to 1, means 0 plus 1. So for example, in this case this number always comes by having k is 3, and the formula for this is when x is less than equal to 3, it means probability of 0, 1, 2 and 3 is there, and here the probability is 0.6. so 0.6 and k3, you read the cumulative probability equal to 0.663. So it is not calculating individual probability, it is calculating the cumulative sum of the probabilities up to 3, threshold number 3. For example, if I have to calculate up to 2, then I know that up to 2 would be simple. X is less than equal to 2 means 0, 1 and 2. So this is the number 0.317. We will be able to see if your number of trials are 5 and probability of success is 0.7. So it is up to 3 and it is up to 2. So we can say that possible values would be for random variable would be 0, 1, 2, 3, 4 and 5. And up to 3 means this is the probability we have evaluated, and up to 2 means including 0, 1 and 2. So if you take the difference, you can get the value for the probability for when x is 3, exactly equal to 3. So probability of x equal to 3 would be probability when x is less than equal to 3 minus the probability when x is less than equal to 2. Subtract these probabilities to get the exact value of that probability, and we will see when we'll be using Minitab to do the same thing. And I will go to start using the Minitab, and we will do it in the Minitab in the same way. Let's see, go to the Minitab. Okay, let's do the same thing what we have done in manually from tables and on piece of paper to calculate the probability using Minitab. Okay, so the things are simple. Let's say if I am interested in calculating, I go to the calculator tab, and then I go to this probability distributions. I have so many distributions available. I need to pick a binomial distribution. So here, if you just stay there, you see that this tab provides you the opportunity to calculate the probability distribution functions, cumulative distribution functions, or inverse of a cumulative distribution functions for a binomial distributions. So here this software is no more actually distinguishing between PMF and PDF. So you can use it interchangeably as well. Okay, so this is the tab where you are going to calculate the probability. For example, I just pick it first one to calculate the probability. Not the cumulative, not the inverse cumulative, let's say. And number of trials for this binomial distributions, because we are dealing with 2 parameters. So let's say we take a 5 number of trials, and let's say we have a case of that non-fair coin where 60% is the probability of getting a head. So okay, that is something my parameters. So these 2 parameters I have given, number of trials and the probability of a success, which is 0.6. Okay, let's say input constant. For example, my constant is I'm interested in calculating the probability when x equal to 3 number of heads are coming. So my x comes out to be 3 here. So this is I taken it as an input constant. So if I do this, I have an option of storage, optional storage, where I can store it on a worksheet. But let's say I want to see it on a session window. So if I just click it on OK here, so I will be able to calculate with binomial probability density function with number of trials are 5 and probability of success is 0.6, and my x is my random variable, and when x equal to 3, so your probability would be 0.3456. so this is exactly the same as 5 combination 3 times 0.6 to the power 3 times 0.4 to the power 5 minus 3, that is 2. So if you do it on the on a piece of paper using the formula, you will be able to get this probability when x equal to 3. So this is the way by which you can calculate the probability. Okay, another way of it, for example, if I say x is a random variable, and this is something, let's say p of x is this thing, and here I just say it capital F of x, which is a cumulative, and I just make it like this. For example, here x can take different values, let's say 0, 1, 2, 3, 4 and 5. I just take that experiment where I could have these possible values, and I am interested in calculating the probability here for that thing. So what I do is I go on calculating probability distribution and binomial probability, and here I am interested in calculating the probability. My number of trials are the same, 5 and 6, but input column is not the constant value, but input column is actually C1, which is having values 0, 1, 2 and 4. That is what I select, and output column is I select as the column 2, where I'm going to store the corresponding probabilities. So if I press OK, I will be able to calculate the probability when x is 0, and when x is 1, and x is 2, x is 3, and you see at x equal to 3.3456, the same is that number when x is 3. So this is actually representing this cumulative probability, and once you know the random variable and you know the corresponding probability, quite simple, you can draw the probability distribution table as well, just by graphing these two variables. So I'm not going into that. Okay, the second thing is the sum of those probabilities. For example, in that table, when n was your 5 and you have gone up to 0 to 3, so you need to take a cumulative values. Cumulative values can be calculated. Go to the calculate probability distribution binomial, and here instead of probability I'm interested in cumulative probability, and my input column is x here, but my output column I want to represent store it in that column 3. So if I just do that, I will be able to see that cumulative probability distribution. So this is exactly the same values which are given in your table as well. When x is 0, 0.01, 0.08, 0.37, if you just go to that table, if you look back your previous lecture in that table, so when x is 0, 0.1, 0.087, 0.317, 0.663, 0.922 and 1. So all these values are available in that as well, 0.92 and 1. So this is how you can calculate the corresponding probabilities as well as cumulative probabilities. Another way of calculating the probabilities and the cumulative probabilities is by looking and visualizing the probability. Here you have just calculated this tab, calculation tab, but what you do is if you go to the graph tab and here you want to plot the distribution of the plot, let's say probability distribution plot. So if you just stay there, you can see that view and compare the shape of the distribution or calculate probabilities and associated x values. All these things you can do it. Just click on that, Once you click on that, you will be able to get that window, which is actually talking about whether this distribution is a single, varying the parameter, two distributions, or comparing two distributions, or view probability. For example, I just select I am interested in viewing the probability. So for example, I know up to x is when k is less than and equal, x is less than equal to 3, your probability is 0.66304. That is what I am interested in. Okay, I just click on this view probability, and then this window comes. Here first I have to select the distribution. My distribution here is binomial, and number of trials are 5, and the probability of success is, let's say, 0.6. And then I go into this tab of shaded area. Okay, what type of let's say the shaded area to be defined with probability or x value. So for example, my x value is 3, or threshold is 3 or less than 3, and I have less than and equal to 3. So I take the left tail test. If greater than 3, then this one to be taken. If there is both tails are there, or if the middle value means the greater than x1 and less than x2, then I take here. So here I have to take the left tail test, left tail value, because I'm interested in values of the probability where x is less than and equal to 3. So I just select this, and my distribution is binomial with that, and my shaded area is left tail with threshold value of 3. Then just click on. So if you just click on, you will be able to see that for 5 number of trials with probability of success 0.6. So this number comes out to be 0.6. The same number comes out to be 0.6. So, and this number you can make it a little bigger. Yeah. So this gives you 0.663 is actually when x is 0, x is 1, x is 2, x is 3. So when x is 0, your probability is 0.01. When x is 1, your probability is something 0.0768, this value. And when x is 2, your probability is 0.2030, 0.2030. And when x equal to 3, when your probability is 0.3456. So at x equal to 3, your value is this. And for cumulative probability, when x is less than equal to 3, represented by this shaded area, and this comes out to be cumulative probability 0.66304. So this is how you can use Minitab to calculate probability as well as visualize the probability distribution. Okay, in that case, we will go into one more way of looking at graph, probability distribution, vary parameters. So if you look at varying the parameters, so I am picking up here my distribution binomial, and number of trials, let's say I just make it, if we go back our earlier lecture like this one, where we have such a situation in which, okay, this one, let's say, when your number of trials are, okay, P is 0.25, number of trials are not mentioned, but I just take it 0.25, 0.5 and 0.75. Okay, this I am interested in doing on Minitab. So what I do is number of trials, let's say I got a 12 number of trials, and event probabilities are 0.25 and 0.5 and 0.75. If I do like this, and what I want is the multiple graphs, so in separate panel of the same graphs, overlaid on the same graph on separate graphs. In separate panel of the graph, I have 3 options for these 3 different graphs in a separate panel of the same graph. Let's say I just do it like this. Okay, once I go on number of trials with these event probabilities, so you can see that I can show that I can see that when P is 0.5, I mean, if I go to the editor toolbar, may I go to this editor toolbar, layout tool? Okay, but once you have separate graph, then you can do that. Okay, forget about it right now. We will show you later about this option as well for laying out. Let's say here you see when you have a probability 0.5, then you have a symmetric distribution, and when you have 0.25, then you have right skewed, and if you have 0.75, then you have left skewed. So the shape of the distribution changes if your probability of success changes in different distributions. So all these distributions are representing the random variable and their corresponding probabilities, and we can see the variation in different probabilities. One more thing we can do is we solve that last lecture problem, that this problem in which we have a number of trials are 18 and probability of success is 10, and we are interested in exactly two pollutants. So this is the number which let's say I'm interested in. So how to do it on Minitab is just go to calculate probability distribution binomial, and your number of trials are 18 and your probability of success is 0.1 in that problem, and input is let's say you are interested in exactly two inputs. So once you press that, you will be able to get 0.73376 when x is 2. So let's see, when x is 2, then 18 combination 2 is 0.284. So okay, properly I have not the probability but the cumulative. I go back again, going to that binomial. Okay, because that was cumulative. Now I need to know probability. I just press it again. So I got this 0.28 is the probability when number of trials are 18 and probability of success is 0.1, and x is equal to 0.283152. So that is the probability I got it in this particular problem. When second part, the probability of at least 4. So at least 4 means this 0.098 I got it. So at least 4 means x is greater than equal to 4. So what I need is to go to this graph toolbar, greater than 4. So I just visualize probability distribution, view probability, and here I select 18 is my number of trials and 0.1 is my event probability, and shaded area I want it at least for greater than 4. So I means I need to go into the right try, and value is greater than 4. So my threshold is x value is 3. X value is greater than 4, at least 4. I think it's in the problem is yes, greater than or equal to 4. Okay, so I just select 4 here and just press it. So I will be able to see that 0.00982, which is just show it in bigger, 0.0982, that is actually the probability I calculated. 0.098, that is the probability I calculate when x is greater than equal to 4, when your number of trials are 18 and probability of success is 0.1, and this is your probability distribution. So table, and this would be your probability when x is greater than equal to 4. So all these things, for example, in the next part where your problem was in the range from 3 to 7. So greater than equal to 3 and less than 7. So if let's say I have to calculate this thing, I can do it from graph, probability distribution plot, view probability plot, shaded area to be in this range. So x value should be greater than 3, okay, and less than 7. So 3 to 7. 7 is actually included here, but here 7 is not included. So less than 7 means go up to 6. So 3 to 6. If I just see that, I will be able to calculate from 3 to 6. So 0.266 is actually the this red area is 26.5% is the probability from, okay, we have this is 26.5% is the probability from 3 to 6 actually. So this is we have calculated on a Minitab as well. So I have shown that all the problems which you have solved on a piece of paper, using tables, and using Minitab. And the same thing you can do it on Excel as well. So this is where I stop this lecture, today's lecture.